Hi guys. I decided instead of uploading the notes, because I think somebody took them to copy stuff down and didn't give them back to me by accident, I'm not sure, I can't find them, that I would make a video on section 2.1, and just in case you need it for reference, future reference, okay? So we're going to be talking about quadratic functions. Essentially that's going to be the crux or the topic here, but we have to also consider the fact that these functions that we've been working with, these basic functions, many of them are polynomial functions. So I want you to remember that we had a constant function, right, which is just, mathematically it's denoted f of x equals to c, where c is a constant or a number, such as, f of x equals 2 or y equals -1. These are just horizontal lines that go through the y-axis at the particular point. So for example, f of x equals to 2, well, that's going to cross through the point 0, 2 right here, and it's just going to be a flat horizontal line from negative to positive infinity. And likewise, y equals to -1, same thing. We're going to intercept 0, -1 right here. So we're crossing the y-axis, that's a y-intercept, and we're going to draw a horizontal line through that point. That goes on and on forever in both directions. Well, did you know that a constant function is a polynomial? It may not seem like it because I know poly means many, but we're going to revisit that again in a second. Linear functions, of course, those are functions of the type y equals to mx plus b, or f of x equals mx plus b. Alright, so maybe, we have something like 3x minus 1 or x minus 2. Very simple linear functions. And, we can graph these. We can use rise over run. Right here I plotted the y-intercept at 0, 1. And I rose up 3 and went over 1 and plotted the other point here and connected it with a straight line. Likewise over here, I have a slope of 1. We don't write that 1. And so we go ahead and we plot the y-intercept 0, -2, and from there we rise up 1 and over 1, plot another point, and then connect them with a straight line. Those are linear functions, which are also polynomial functions. And then finally, the thing we're going to focus on the most in this section are the quadratic functions, and those are functions of the form f of x or y equals x squared, okay? And this is the parent function here at the origin. And why are they all polynomials? Well, because by definition of a polynomial, which is right here, this big long ugly equation, if you remember from class, I said that these powers up here have to be positive numbers, okay? We have this a sub n x to the n plus a to the n minus 1, x to the n minus 1, and on, all the way until we get down to a constant, so some number, right? And, if all of these are 0, then this would be the linear term right here, right, x to the first power, and this would be the constant function. So if all of these coefficients were 0, then we'd be left with just, y equals something here, some number, that would be our constant function. And if everything here was 0, but maybe we had x plus a number, that would be the linear part of the polynomial. So even though we have something like y equals 2 or y equals 3x minus 1, even though they only have a few terms, they're still considered in a class of polynomials. Okay, so just keep that in mind. We always write a polynomial function in descending order. So what that means is we always start out with the highest power of x and then drop down to the next one, right? And then the next one, and then the next one. This n minus 2, n minus 1, and those are powers of x. We start with the highest and we write it in order of descending power. This a sub n is called the leading coefficient because it's being multiplied to the variable of the highest power. Okay, so a sub n is called the leading coefficient. So for example, you might on a test get something written like this, and you notice 2 is here, and x squared, and x cubed, and it's a mess. So if we want to write it properly, then we start out with the highest power, which would be negative x cubed, and then we go down a degree, right? This is called degree, okay? And so the next power down would be negative x squared, and then we want x to the first, and then the constant last. So this mimics this thing here. The leading coefficient in this case would be -1, because a -1 is being multiplied to the variable with the highest power or degree. And we would call this a third degree polynomial because the highest power is 3, or degree 3. Okay? I didn't write all the notes in advance, but I did write many of them, so I will be writing at some point. Okay, so that brings us back now to quadratic functions, right? That parabola, where we have f of x equals to x squared. And the standard form, or the general form, of the quadratic function is y equals, or f of x equals ax squared plus bx plus c. And there's a stipulation that a cannot be 0. Because if this leading coefficient is 0, then this whole term becomes 0 here. And if this goes away because it's 0, then we're left with a linear function. So quadratics specifically state this restriction, because if we plug 0 in for a, we're not going to have that term there anymore, and we're going to end up with a linear function. Okay? And the properties of the quadratic function, graphically speaking, are the following. The graph is a parabola. It looks like a U-shaped graph. It's going to open up or down, depending on some things, which I'll talk about in a second. Parabolas have a vertex, so here the vertex is at the bottom, and here it's at the top. That means the vertex here represents a minimum, and the vertex here is going to represent the maximum. Okay, the top of the mountain, the bottom of the bowl. Okay. If a, that leading coefficient, is positive, if it's a 3, a 5, a 2, whatever, or even a 1, then our parabola is going to open up. And that means the vertex is going to represent a minimum. And if a is a negative value, then that means that our parabola is going to open down, and the vertex would be the top of the mountain again, so that would be a maximum value. Okay? The axis of symmetry is the x-coordinate of the vertex. So maybe I shouldn't have put this here so soon. Let's change this for right now, because we're not in standard form. Oops. The axis of symmetry is a line. Okay? It's a line. And it's the x-coordinate of the vertex. So it's going to be the equation x equals whatever that x-coordinate of the vertex happens to be. Now if a is bigger than 1, you're going to get a vertical stretch. I demonstrated that with the calculator in class, and I'll do another one right now. And if a is between 0 and 1, in other words it's a proper fraction, like a half or a third or 3/4, then you're going to have a vertical compression or a shrink. So right now I am going to just switch over to the calculator, and I'm going to put the parent function x squared in, and I'm going to put 2x squared in y2, and I'll put 5x squared in y3. And let's just have a look at what happens. So the, oops, got to change my window, zoom 6. Zoom 6. I don't know what my calculator is doing. Zoom 6. There we go. So here's x squared, the parent function. Now, when the coefficient is 2x squared, the red graph, it gets thinner. And for the third graph, that's 5x squared, it gets even thinner. So the bigger that our a becomes, the thinner the graph of the function is going to look. And what that means is, if you can think of holding the ends of a jump rope and putting your foot on the bottom so that your hands are even, so you have this U-shaped jump rope, and as you pull up on the handles, the graph gets skinnier and skinnier and skinnier. That's called a vertical stretch. Now, if I change this to say, I don't know, 0.25 and x squared, and I change this to maybe 0.33 x squared, or maybe 0.75 x squared. So what I'm doing now is I'm making this proper fraction, a fourth, a third, 3/4, and the parent function. what I should notice is that my graphs are going to get fatter. So here's x squared. Here's the second one. So it's wider, or I call it fatter. Here's the next one, 1/3. And then here's the other one, 3/4. So this one right here, real close to the parent function, that's almost a 1. Right? When x is equal to 3/4 or 0.75, it's almost going to be the same as if it were 1x squared. But as I get further away from 1, you notice the graph gets wider and wider. So when a is between 0 and 1, a proper fraction, then you're going to have this vertical compression, and graphically it's going to look fatter or wider. And it's also called a shrink, okay, a vertical shrink. The standard form, which we like to work in, or the vertex form, is this form, a times the quantity x minus h squared plus k, where the vertex is the coordinates hk, and the axis of symmetry here now in this form is the line x equals to h. Okay? So, we often want to rewrite from this form to help us either graph it or understand, find the vertex, understand some things about it. And to do that, we're going to have to complete the square. Okay, so I put an example that I believe I did in class, this one here. And I said if f of x is equal to 3x squared minus 6x plus 4, identify the vertex and the axis of symmetry. Well, I could do that one of two ways. I might say, rewrite in standard form. Maybe that's one. And then 2, identify the following. Okay, well first if I want to rewrite this in standard form, I'm going to have to complete the square. So I'm going to rewrite this like so. So remember, we're going to only focus on these two terms, the terms containing x, initially, and then we're going to combine that with this 4 and some other things. So the idea is this. First and foremost, you can never have a number here other than 1. So in this case, I've got to factor out a 3, and I'm only factoring out the 3 from these two. So if I factor out a 3, I'm going to be left with x squared minus 2x. And then I told you put a box. Squared plus 4, and then if we're going to add something squared here, we need to subtract that something squared over here. Furthermore, since I factored out a 3, if I were to FOIL this back, or distribute this back, this 3 is going to distribute to whatever number is here. So I have to multiply this by 3 as well. Okay? So, to complete the square now, what we do is we take half of the linear term, so half of 2 is 1, and we square it. 1 squared is 1. So if I'm adding 1 here, I have to subtract 1 over here, but not just 1, 3 times 1, because I can't forget, 3 times 1 here is 3. This forms a perfect square trinomial, which is right here. This is the perfect square trinomial. It's a perfect square trinomial because x squared is a perfect squared and 1 squared is a perfect squared. So the idea here is we're going to rewrite this perfect square trinomial as, so I'm going to do it the long way here, as though you're factoring this down. So it'd be x. If the second term is minus, you're going to have a minus here, and then there's 2 1s, so you put a 1 here and a 1 here. And I'm going to clean this up. This is plus 4. Minus 3 times 1 is minus 3. Now this, we're going to go ahead and condense down and write it as 3 times x minus 1 squared. 4 minus 3 is 1. So, now I can tell, since I'm in standard form, I know I'm going to have a vertical stretch of a factor of 3. Why? Because a is bigger than 1. Right? I also know that the vertex is going to be at the point 1, 1. This is h, this is, h, this is k. And I also know the axis of symmetry is going to be the line x equals 1. It's the x coordinate of the vertex. Okay, one more little completing the square problem. We're not going to identify a vertex or anything, but let's just complete the square. So I don't know, 2x squared plus 12x minus 3. Okay, so again, I'm going to focus on these two, and I've got a 2 here, so I'm going to factor that out. So I'm left with x squared plus 6x plus a box squared, right? And then minus 3 minus a box squared. Now since I factored out a 2 here, I need to multiply 2 to this box over here. And I take 6 and I cut it in half. Half of 6 is 3, and if I square it, that's a 9. So if I'm going to add 3 here, I've got to subtract that. I'm going to put that same number in the box on both sides. Just one's added, one's subtracted. Now I have a perfect square trinomial, so I can write this as 2 times. Now you don't have to go through this step when you're working this out, but I'm just trying to show you that, you know, this is plus plus, so this is going to be plus plus, and I've got 2 3's here, so a 3 goes here and a 3 goes there. And since these two are the same, I can write it like this. X plus 3 times x plus 3 is the same as x plus 3 quantity squared. Over here now I've got negative 3. Now negative 2 times a positive 9 is a negative 18. So what I've got is 2 times x plus 3 quantity squared. The signs are the same, so I'm going to add and keep the same sign. And that would be my function in standard form. And if I wanted to identify the vertex, we'll just do it. The vertex is negative 3, negative 21. Also, the axis of symmetry is the line x is equal to negative 3. And I also know that this thing is going to stretch by a factor of 2 because a is greater than 1. It's also going to open up on the graph because a is positive. And by the way, I'm just going to graph this just so you can see. So let me get the calculator here. And I'm going to put it in just as I see it. Let me just move that over a little bit. So you can actually put it in your calculator right here. So I can do 2 times x plus 3 quantity squared minus 21. Now if I hit the graph key on the window that I'm on, I'm probably not going to see the vertex. It's way down there at negative 21. So if you want to change that, just press your window, and I don't need to move left or right in the x direction to see. I need to move in the negative y direction to see. So I'm going to scroll down to y min. I'm going to make it negative 22. I always go a little bit past the value and hit graph, and there it is. Okay? And if I'm curious about that vertex, I can do second calc. Now it's a minimum, it's opening up, right? Just like I said. So second calc minimum, which is 3. And I'm going to arrow a little to the left of the bump and press enter. Arrow a little bit to the right of that vertex or bump, press enter. And I'm going to press enter one more time. And look at that. The vertex is at negative 3, negative 21, just like we said. Okay, but you need to know how to do it with the calculator and without. So anyway, that's a little calculator practice for you. Okay, finally, I'm just going to go through the book here to make sure I don't forget anything. Finally, we're going to talk about finding maximum and minimum values. Okay, so this is on page 119. Okay, so to finding maximum, I'm going to abbreviate it, minimum values. Now when they ask you for the value, they're asking you for the y coordinate. Okay? Oops, sorry, this is going out of focus here. It's just doing this by itself all of a sudden. I don't know why. I don't know how to fix it. Oops, I just messed it up. There we go. So, when they're asking you for the value, they're asking you for the y coordinate. And remember I showed you that, you know, in the general form, ax squared plus bx plus c, we'll say y equals. In that form right there, you need to be able to identify a, b, and c But mostly for this little formula, you just need a and b. And the formula goes like this. It goes x is equal to negative b over 2 times a. Alright, so if that's x, then y is equal to f of negative b over 2 times a. So if this worked out to be a 2, let's say, then you could plug 2 into the original function to get the y value. That's the height of the function. So back to this problem here, for example. Suppose I'm taking a multiple choice test and I'm asked to identify the vertex. And I really hate completing the square. Well, you can use that. So let me just rewrite this over on this page. The function was y equals 3x squared minus 6x plus 4. Gosh dang this thing. What's it doing? I'm sorry. I can barely take it anymore. I don't know what's going on here. Fix. It does not want to cooperate with me. Let me try something else here. I apologize. So look, a is 3 and b is negative 6. So I can use this and find the x-coordinate of my vertex by saying negative b. Now b is a negative 6, so you're going to plug that negative in. This is getting on my last nerve. OMG. Over 2 times a. Well, a is 3. If I clean this up, the opposite of a negative makes that a positive. 2 times 3 is 6. So the x-coordinate is 1. Now, if I want to find the y-coordinate, or the value, the maximum value, I know this parabola is going to open up somehow because a is positive. I know it's going to be skinnier than the parent function because a is bigger than 1. But, I need to know what the vertex is, and I don't want to complete the square. So how do I find the y-coordinate of the vertex? I take what x is and I plug it in for every x. So I can say y of 1, or if you like to write it as f of 1, they mean the same thing. That's equal to 3 times 1 squared minus 6 times 1 plus 4. 1 squared is 1, so 3 times 1 is 3, minus 6 plus 4. And 3 and 4 is 7, minus 6 is 1. So what I know is that the vertex now has coordinates 1, 1. And my axis of symmetry, well, that's just x equals the x-coordinate, of the vertex, right? And if you look back to the problem, that's exactly what we found for this one. We found that the vertex was 1, 1, and the axis of symmetry was x is equal to 1. Okay? Now, one thing that I skipped over accidentally, which I'm going to talk now, is the zeros, which is the same as the solutions, which is the same as the x-intercepts, which means the same as the roots. So you're going to see different words throughout the course. The place where the parabola is going to cross the x-axis. Why? Because, if I use this, I know I've got a vertex. If I make a sketch, at 1, 1, I know the vertex is there. I know this thing opens up, and so I could kind of go like that and say, well, it looks kind of like that, and my axis of symmetry is this line right here. Alright, but we might want to get a little bit more precise. Now, this particular function from above is going to be not hitting the x-axis at any point because it's opening up and it's already shifted 1 unit above the x-axis. So that's a bad example. But if I want to find the intercepts, then what I need to do is I need to factor my function. So for instance, I'm trying to find one here real quick in the book. So f of x equals negative x squared plus 6x minus 8. All you have to do, is take the function and set it equal to 0. So write negative x squared plus 6x minus 8 equals 0. Now, there's something other than a positive 1 there, so we need to multiply through both sides by negative 1, and that's just going to change the signs of everything. So multiplying through by -1 is going to give us x squared minus 6x plus 8 equals to 0. And now we can see, can we factor this? Well, what are the factors of 8 that when I add or subtract them give me a 6? Dang this thing! Well, 4 times 2 is 8, and 4 plus 2 is 6, right? We have a negative there. Whenever the second term is negative and the third one is positive, we're going to have minus in here. So, if I do 4 times 2, and I FOIL it back real quick, I see I get x squared minus 2x minus 4x. Negative times a negative is a positive 8. And if I combine those, I'm going to get negative 6x. So I factored correctly. So I have x minus 4 times x minus 2 equals 0, and that means you take each one of these and set it equal to 0 and solve. So we get it x equals to 4 and x equals to 2. Now those are just the x values, those are not the intercepts, because the intercepts are points. So what we would write is at 2, 0 and at 4, 0, those would be the x-intercepts. Okay, and that was 2.1 in a nutshell. So you'll let me know tomorrow in class if you have any questions, and I'll see you then.